Hello everyone and welcome to Keeping Tabs on Chemistry. In this video we are going to be talking about electrolytes. So an electrolyte is a substance that dissociates into ions in solution. So typically we're talking about some sort of solid that when it comes into contact with water it's going to break apart into ions. That's what dissociate means, to break up into ions. So something like our table salt, sodium chloride, when it's aqueous, so when it's in solution, it separates into Na plus and Cl minus. So you can kind of see here would be a cation, like the sodium surrounded by water molecules, and the chlorine and anion surrounded by water molecules. So where we originally had a nice lattice structure solid, the water molecules are going to break it up into its ions in solution. So if we had a beaker with this sodium chloride, what would it look like inside? So I would see a sodium ion, a chlorine ion, sodium and chlorine ion, sodium and chlorine ions. What I don't see is any of the original NaCl compound. It is all sodiums, the cations, and chlorines, the anions. So all of our ionic compounds are electrolytes. Remember, ionic compounds are those metals and nonmetals, right? So sodium chloride is ionic and it is an electrolyte. Now, a non-electrolyte is a substance that may dissolve in solution, but it will not dissociate into ions. So, sugar, C6H12O6, will dissolve in solution, so it'll be surrounded by water molecules and it'll break up into different pieces so that I can't actually see the sugar cube anymore, but those are still entire sugar molecules. There's no ion here. There's no H plus or O2 minus or I don't know, carbon plus 4. It's still an entire C6H12O6 molecule, just broken up into pieces that we can't see the difference anymore. So the difference here is that most of your covalent compounds are non-electrolytes. Things like sugar, right? All nonmetals are going to be non-electrolytes. Now, it's not all covalent compounds. We're going to talk about acids and bases in this unit, which are arguably covalent or ionic, but they are electrolytes, not non-electrolytes. So some compounds dissociate into ions better than others. So we can differentiate electrolytes into strong and weak. So strong electrolytes will dissociate completely into ions. That is 100% ions. So sodium chloride breaks all into Na plus and Cl minus. So in my beaker, I see Na plus, I see Cl minus. There is no NaCl, the original compound. Right? A weak electrolyte will dissociate only partially into ions. That's less than 100%, which means I'm going to have some of my original compound left over. So here is hydrofluoric acid, HF. HF is a weak electrolyte, so when it dissociates, I'm going to have my original HF, some H plus cations, and some F minus anions. So if I look in my beaker, I see HF, I see H plus, I see F minus, HF, H plus, and F minus. So there's still some of that original because it only partially dissociated into ions. Now you can tell the difference between a weak and a strong electrolyte by testing how well it conducts electricity. Electricity is the motion of electrons. So where do we get availability to move electrons? Well, that comes from having charges in our solution, from having ions. So I can look at three different situations. I can have something like ethanol, which is a non-electrolyte. So there are no ions in that solution. So when there are no ions, there's no way for my electrons to move from one plate to the other. And so there's no light here, right? There's no conductivity. I can't light my light bulb. This is an open circuit, right? There's no continuity for the electrons to flow. Now, KCl, this is an ionic compound, right? It is going to be a strong electrolyte that breaks up completely into ions. So I've got lots of ions available to connect the two different plates. So this closes the circuit and I end up getting a bright light. Right? Now, on the other hand, acetic acid is a weak electrolyte. It has low conductivity, so there's still ions there. There's still availability to close the circuit, but it's just not as good as a strong electrolyte. So for a weak electrolyte, we end up seeing a dim light. So the difference between dim and bright is the difference between weak and strong. So, to end our lesson, we have a practice here. Identify each of the following as a strong electrolyte, weak electrolyte, or non-electrolyte. So we are going to use this conductivity to help us identify this. So here I've got KBr, that's an ionic compound. Bright light, it is a strong electrolyte. Now, the question doesn't ask you to do this, but I'd like to elaborate a little more. So if it is a strong electrolyte, if I were to take, my magnifying glass and look into my solution, I would see K pluses and Br minuses, right? No KBr, dissociated completely. Now C2H4, right, I see that this is covalent. There's no light. This is a non-electrolyte. So in my solution, there's only C2H4, no ions whatsoever. Nothing's really changed. For the next one, HNO2. All right, this one has a dim light, which means this is a weak electrolyte. It's going to dissociate partially. So in my solution, I'm going to have my original HNO2. I'm going to have H pluses coming off, and then nitrites, NO2 minuses as well. And the last one, calcium hydroxide, that's ionic. It's got a bright light, so that is a strong electrolyte. I'm going to see Ca2 pluses and OH minuses in the solution. And that concludes our lesson on electrolytes.